We will now look at the preparation of allyl halides. And this will sort of set a tone for all future chapters when we will first look at the ways to prepare certain class of compound, and then we'll look at the transformations, chemical transformations that class of compound undergoes. When we talk about preparation of alkyl halides, we already know one way to prepare them, and this is the radical halogenation. Although radical halogenation is a reaction that the first reaction that we learned, it is actually not very frequently used in industry because it gives mixtures of products. We have a radical chlorination. Because of its poor selectivity, it will give us a mixture of products, even for very simple compounds such as propane. So we'll get 1 propane and 2 propane, and then a mixture of polychlorinated propanes as well. And very quickly this will lead us to a mixture which is virtually inseparable. The additional problem with chlorine, which is a little easier to handle in industrial settings, is the fact that it's a gas, so it's difficult to control the amounts of chlorine that you use. And so in general, chlorination is not a very useful reaction in industry, but there are some cases when this does work. And these are cases when there's very few or virtually no option for different products. If you have a cyclohexane, which is symmetric, then we can get to monochlorocyclohexane about 50% yield. And once these reactions do work, they're really favorable in industry because the starting materials are very cheap. Chlorine is obtained from sodium chloride, and most of the hydrocarbons are obtained from petroleum, so they're very, very cheap feedstock materials. Bromination tends to be more useful than chlorination because bromine is so much more selective, so we can get this D-butyl bromine is about 90% yield by simple radical bromination. And this shows we owe this to the fact that tertiary position is much more reactive. However, bromine is much more expensive than chlorine, so industry doesn't really like using bromine very much. However, since bromine is more selective and it's also a liquid, which is easier to handle in a small lab setting, it is much more frequently used in academic settings. Industrial setting, handling gases such as chlorine is not such a big problem, so chlorine can be used as well and favored in industry because of its low cost. But overall, the point here is that radical halogenation has a very limited scope in useful preparations of halogenated hydrocarbons. A method that is related mechanistically is the allylic bromination, which is much more frequently used. And if we have this allylic bromination is related to the so-called allylic position, which is the position is an sp3 carbon right next to the double bond. And what happens when we have those sp3 carbons which are right next to the double bond, bromination of those positions is very selective. So even though there are multiple secondary positions in this hydrocarbon, it will selectively brominate only the one right next to the double bond. The question is, why does this happen? Well, if we look at the intermediate in this process, which is a radical, just a radical halogenation just like any other, then this radical is resonance stabilizing. So we can draw an arrow here to give us a radical with a terminal carbon, and this explains the stability of radicals that are based on our system. Okay? So in such cases, we can selectively get bromination in this position, about 80% yield. However, if we have two allylic positions which are asymmetric, such as if we have a methyl group here and a methyl group here, even though allylic bromination favors such positions, we will still get a mixture of about 1-to-1 of these two compounds, since the stability of corresponding radicals is very complex. Okay? Mechanistically, this works the way we've already seen it to work. So the two propagation steps. The first one starts with the reaction of bromine radical with the abstraction of hydrogen, so we get HBr plus this radical, which now has the radical center right next to the double bond, and then the resonance structure can place this radical over here as well. Now, important point to note here is that either of the two resonance structures can react with another molecule of bromine. And the first one will give us this compound, plus Br dot, while the second one will give us this, which in this case is the identical compound, but this could be a different compound. In those cases, we'll refer to such product as allylic shift. So in cases when our resonance structures are asymmetric, we can get two products by two different resonance structures react. Now, as an experimental note, these reactions should not be performed in the large excess of halogen. And the reason lies in the fact that halogens can react with double bonds. I know that's some reaction we'll talk about later, that the concern does remain that these reactions need to be performed with very small amounts of halogens. To do that, a compound known as N-bromosuccinimide also known as its abbreviation NBS, can be used, which reacts with the HBr side product to give us the simple succinimide and the small but constant equilibrium concentration of Br2. And this is how we avoid the rounded product. Now, halalkanes can also be made from alcohols, or alkenes. But these reactions relate to the classes of compounds we haven't talked about yet. We'll mention them later. But at some point we will start seeing this picture is emerging that many compounds are sort of cross-linked on this reactivity chart, and we can get halogens from various different classes of compounds. That concept, by the way, will become very important later on when we start talking about the synthesis, where we aim to combine multiple reactions that we know into a synthetic sequence, which gives us a product from starting material that it could not be directly obtained. Starting to build up for that will be already next topic when we'll talk about the first reaction of halalkanes, the substitution reaction.